All right, I'm going to go ahead and get started. My name is Baron Schwartz. I'm with Percona. We help our clients build fast, reliable, scalable systems with MySQL. I'm also co-author of High Performance MySQL, second edition. And if you haven't picked up any sample copies, there's a few left in the O'Reilly booth in the exhibition hall. If you go through the doors and turn left, there should be a few of them left on the table there. I have 2 copies here if you'd like to pass them around or keep them and be greedy or whatever you'd like to do. They might be a hot item. All right, so today I'm going to take a look at the MySQL query cache. I'm going to look at how it works, what it is and what it isn't, and a few myths about it, because there's a couple of common misunderstandings about it, how it uses memory, and how to tune it and configure it, monitor it, all those things. It's actually a fairly simple system, but there's a couple of, specifically a couple of terminology issues that make it kind of easy to misunderstand. And then we'll dive a little bit into some of the specifics of how it really works at the low levels, especially with InnoDB. And feel free to raise your hand at any time and ask me questions. The slides will be on the O'Reilly website. I submitted them last Friday. I don't know when they go live. Okay, so the query cache caches the result of a select statement. And by that I mean it caches the actual bytes that will get sent back to the client connection. So if there's a cache hit, it just resends those bytes. It doesn't parse the statement. It doesn't optimize and execute. It literally just stops the execution. It's a short circuit in the query execution. And then it sends the bytes back across the wire. It does not cache execution plans. And the reason I mention this is that other database servers have various types of caches. And the most common is caching the execution plan or some sort of fragments of the execution plan or a normalized version of the execution plan. Those other database servers are saving the work of looking at statistics, trying out various query execution plans and finding the best one. So there is benefit to doing that, but there's even more benefit to just not executing the query. Oracle, I believe, now maybe somebody can confirm or deny this, Oracle in more recent releases has something analogous to MySQL's query cache, where they're actually caching the results of the statement. Is that true or false? Anybody know? Okay, it's just a rumor then. Okay, so it's a big hash table. It's a little more complicated than that, but it really is just a big hash table. And the key into the hash table is the query text, the current database, the character set correlations. There's a few other things that go into it. Anything that affects the client's state. The query cache should not change the semantics of the server. So if there is anything different about your connection than there is about the connection that created the results that are stored in the cache, you should not see the cached results. It's case sensitive. It's white space sensitive. Literally, the key into it includes the exact bytes of the select query that you send to MySQL. I have a little diagram here. On the left, we have the little person diagram, and he sends some SQL into the server, which is the big blue rectangle. The first thing that the server does is it checks to make sure that the query starts with the, case insensitively, starts with the letters SEL. That's as much parsing and checking as MySQL does on the query. So if it starts with SEL, then it's probably a select statement. And it's reasonable to check in the query cache and see if there's a stored result there. If there is, we'll get to that on the next slide. If there's not, it goes into the parse, optimize, and execute cycle of the query's lifespan. As the server generates results, yes?
Does that mean my query started with, say, an opening bracket, like an opening parenthesis, which is not query cache sensitive?
There is some special case code for unions which may start with an opening parentheses, and I actually didn't understand that part of the code when I looked at it, so I don't want to tell you a lie. So it goes into the parsing, optimizing, and executing, and as MySQL generates results, it incrementally sends them as soon as they are available to the client. It doesn't generate the entire result set and then send it. It generates a row, sends it, generates a row, sends it. And if the query is cacheable, those result rows, or the bytes that make up those rows, go into the query cache for future statements to return. So if there's a query cache hit, it looks like this. just completely cuts out all of that parsing, optimizing, and executing. So not all queries are cacheable. First of all, only select queries are cacheable. You can't cache an update for fairly obvious reasons. But there's a bunch of other things that make them not cacheable. Basically, anything that makes the query non-deterministic makes it not cacheable. If there's a chance that you could execute the query again and get a different result, it's not cacheable. So user variables, if there's a user variable included in the query, then it's not cacheable. Any non-deterministic functions, things that rely on the current time of day or something randomly generated. Column level privileges. Now this is actually a big one. Column level privileges can introduce a significant query parsing query execution overhead, and they disable the query cache. And the reason for that is that, again, MySQL does not change the semantics of the query. So it has to understand all about your privileges as well. So for example, let's say that somebody says select star from a table, and then someone else comes in and they don't have privileges to that table. They should not see the cached result set, right? So MySQL, part of what it stores in the query cache is a structure that represents your privileges on the tables that are involved, along with some other metadata. And it does do a privilege check before it sends you back the result. However, column level privileges will disable caching and returning those results. Certain kinds of locking statements, which you will mostly use for InnoDB tables, those will also could affect the semantics and disable the query cache for a particular query, and user-defined functions. And there's a variety of other things. There's a complete list on the MySQL manual if you're curious. So here's a couple of query cache myths. The first one is that you might store select star from table into the query cache and then run select SQL no cache star from table and get that result back from the cache. You can't do that. That doesn't work because SQL no cache did not exist in the first query, so the hash key lookup fails and your query goes through the execution pipeline. Perhaps I should actually take a moment here and explain what SQL no cache is. SQL no cache is a hint that you can add into the query statement to tell the server whether you want something to be cached or not. By default, if you have the query cache enabled, which we'll get to later, MySQL will cache any select query. You can also explicitly disallow by saying select SQL no cache star from table, or if the query cache is enabled only on demand, you can explicitly request that the server cache something by saying select SQL cache star from table. Okay, the second myth is that MySQL doesn't check the query cache if the query contains your favorite non-deterministic function. That's not true because MySQL doesn't parse the statement, so it doesn't know. So this actually feeds into my next slide. The query cache has overhead. So the point of the query cache is so that you don't have to re-execute statements, right? And the best case scenario for getting efficiency out of the query cache is when you have a statement that has small results that are very expensive to generate, right? So you get the high performance to cost ratio. If a query takes a really long time to execute and is easy to store in the cache, then storing it in the cache saves you a tremendous amount of work. However, it's not all roses. There's always some overhead. There's overhead on every select statement because you have to check the cache for a hit. And if it's uncacheable and it's not already in the cache, or it's cacheable and it's not already in the cache, then you have to go through the work of actually storing the results into the cache. There's some overhead there as well, and that can be significant. Also, every other type of statement that alters a table that is in the cache has to invalidate or evict those results from the cache. There is some work involved in checking whether there's anything in the query cache that you need to throw out. So every query that you send to the server has more overhead when the query cache is enabled. The point is, though, that hopefully your workload is going to be such that having it enabled saves work rather than adds more. Any questions before we get a little more into the internals? Yes?
What if you have a SQL no cache for an update?
That will be a syntax error because the parser doesn't recognize that grammar. So the question is, what can you say, update SQL no cache some table? That'll be a syntax error.
So you can't avoid throwing in that's going to be caused by an update.
That's right. If you were to say, let's suppose that SQL no cache update was valid, a valid statement syntax, then what that would mean was that you're updating a table and you're leaving results in the cache that no longer match what's in the table. Right? So that would change the perceived behavior of the server. And there was another hand here. Yes?
Yeah, under what conditions would you see that a query cache for read is not recommended?
Under what conditions would you see that caching reads is not recommended? I'll address that a little bit later on. Okay? Okay, so the query cache is a chunk of memory. And it is completely in memory. It's not on disk. MySQL allocates as much memory as you specify in one chunk when you either enable the query cache or when you start the server, if it's enabled in the configuration file. MySQL allocates that all at once with one big malloc, if you're a C programmer. One big malloc, and then there's no operating system memory management of that after that point. So MySQL manages its own memory after that. And the reason for doing that is because malloc is relatively expensive. So you don't want to be allocating and freeing memory from the operating system every time you've got caches to cache queries to evict or queries to put into the cache. So internally, this big chunk of memory is stored into blocks. And here's where the first confusing part comes in. Because you may be used to, for example, blocks on disk or something like that, or blocks in the memory or pages in memory. This is not like that. This is MySQL reusing a term, probably because they couldn't think of a better term to use for it. Maybe chunk would have been a better term or something like that. But it's not a traditional block the way you may be thinking of it. It's variable sized. It is the size that MySQL actually needs for whatever it's currently doing. And initially, the query cache, however big it is just one block. It's just one big fat block because there's only one piece of memory initially, right? So there could be several different types of blocks in the query cache. You can have blocks that store results, blocks that store the key into the cache, which is the query's text and the character set and the collation and all those kinds of things. You can have blocks that store the list of tables that went into the that the query referred to, those kinds of things. Most of the time, you're probably most interested in blocks that are either used to store the query's results or blocks that are free. So initially, MySQL, when MySQL is storing a result, initially it allocates a block of a size that you can configure. So you can set the query cache min result unit configuration variable, and that is how big of a chunk, aka block, MySQL will initially allocate to put the query into. Let's take the simplest case and say that you've just started and the query cache is completely empty and it's one big free block. It's really easy to find a place to put it. But after you get a bunch of blocks in there, and remember MySQL is doing its own memory management, much like a simple operating system might do, it has to look around and try and find a free place to put a query result. That can take some time. So there's one of the overhead of having the query cache enabled. And then when the server starts generating and sending rows back, it has to store these results, the bytes themselves, into the block. And since the server doesn't know in advance how big the result set will be, because it starts sending results as soon as it starts finding them, it doesn't know how many blocks to allocate. That's why or how big of a block to allocate in advance. That's why it just chooses the size of a block that you have specified and then starts putting things into it. If the query actually ends up being bigger than a user configurable maximum size, the query cache limit, then MySQL says, oh, that one was too big, and it throws it all out and continues to send the rest of the results back to the client. There's another place where overhead comes in. Because if your queries are bigger than, if your result sets are bigger than the amount of space that you want to use for them, first you're going to store them all in there, and then you're going to throw them out. And now you're not going to have anything in the cache for the next time that query comes through. So for each block that MySQL allocates, it shoves results into them, and when it's full, it tries to allocate another. And when it's done, it trims the last block to size if it's not completely full, which it usually will not be. So here's a pretty little picture. On the far left is what the query cache's memory looks like initially. It's one big block of memory with a little bit of, it's supposed to be around 40 kilobytes of memory used for internal structures and those kinds of things. So that's the initial state. The second blue block in the picture is as you've started to store some results. So I'm not sure if that really comes through clearly in the back of the room, but I've got diagonal lines indicating that we allocated some block of memory and we're kind of filling it up from the top. The results are complete in the third rectangle in the picture, and you can see that last block is not completely full, so there's a little bit of free space left in it. And then MySQL is finally going to trim that to size, and then you're going to have like 1.5 blocks used there. Let me rephrase that because I just added to your general confusion. You have 2 blocks used and 1 block free, and you've trimmed the last block to size. Questions about that? Okay. So the next thing is fragmentation, and this is another classic computer science problem. Anytime you've got allocating memory or allocating file systems or anything like that, you can get fragmentation. And there's several reasons that it can happen. The first thing is that it can happen because of trimming, and I'll show you how that works in just a second. It can also happen because of invalidations. You can throw some results out and leave yourself holes in the query cache's memory. And fragmentation is a problem because you can get holes in the memory that are actually too small to fit anything in. So that memory is wasted. The query cache low mem prunes server variable tells you how many times a query has been evicted from the cache because you didn't have enough memory to store something else that you wanted to put in it. So when there's not enough memory, MySQL will throw out the least recently used query and then reuse its memory. And if you see that happening a lot and you have free memory, then something is causing that to happen, most likely fragmentation. So here's how fragmentation can happen. You can have 2 queries being stored at once. So in the second picture, we're storing both of them. In the third picture, they're both done. And in the fourth picture, we've trimmed them both to size. And notice that there's now 4 blocks of memory here. There's one that's got results in it from query 1. There's a free block, results from query 2, and another free block. That free block between queries 1 and 2 is too small to use. It's smaller than that minimum result unit that I spoke of before. So that memory is going to go unused for future stores into the query cache. The query cache doesn't have all that many configuration and status variables. Here are the status variables. There's only a few of them. There's query cache free blocks, which shows you how many of the blue rectangles you have in your entire query cache. The free memory, which is the number of bytes of memory. The number of hits, which is the number of times that a query has been served out of the cache instead of executed. The number of times a query has been inserted into the cache. The number of times queries have been evicted, the low mem prunes. The number of times that a query has been evicted because there wasn't enough free memory. The number of times that a query was uncacheable, including queries that got too big to store in the cache and then were thrown out. The number of queries in the cache and the total number of blocks in the cache.
On the queries that were too big, if you had the same query 20 times, is it going to tell you you had 1 query or is it going to tell you you had 20 queries?
If you have a query that ends up being too big to store into the cache, it's going to go through the same cycle every time of I'm starting to store, oops, it's too big, throw it out. And then it's going to increment the querycache not cached variable. Okay, so we'll go through those in a little bit of detail. The querycache total blocks is, well, perhaps I've already gone through it in this amount of details. The total number of these variable-sized blocks that are in the cache. That's free blocks, that's blocks that hold table lists, blocks that hold results, every kind of block that's in there. The free blocks, you can subtract from that, and you can see how much fragmentation you have in your system. Now, the worst case is that for every block that's being used for something, you've got a free block in between it and the next block that's being used for something. So the worst case, here's the worst case on the far right. You've got 2 free blocks and 2 used blocks. So bad fragmentation is when the number of free blocks is close to half of the total blocks. The query cache free memory is total bytes in free blocks. That's not free blocks, but free bytes. And you can subtract that from the size that you configured the query cache to be and figure out how much memory you have free in the query cache. The number of cache hits. Here's a little convenient little metric for you. The hit rate is the query cache hits as a percentage or as a fraction. It's the query cache hits divided by the hits plus the select queries. Now, why hits plus select queries? The reason is that when there's a hit, the query cache hits variable is incremented rather than the com select variable. When there's a select query that ends up not being satisfied from the cache, MySQL increments the com select variable. So you have to add the two of them together to figure out how many select queries your server actually handled. And we've gone through the query cache inserts and the low mem prunes. Querycache not cached, as I said before, that can be incremented by queries that were bigger than query cache limit. Can also be incremented by any other kind of uncacheable query, such as one that you had the SQL no cache hint in, or if it had a non-deterministic function, such as the current time or something like that in it. On the bottom of the page here, I have the querycache invalidations. I just made that up. It doesn't exist. However you can calculate it, you can subtract the queries in the cache from the number of inserts. So that tells you how many queries have come back out of the cache.
Quick question.
Yep.
For the cache not querycache not cached,
Mm-hmm.
will updates, deletes increment that, or does it figure out that it's a select that wasn't cached?
Good question. So the question is, for querycache not cached, what increments that? Updates, deletes, those kinds of things. No, updates and deletes don't. It's only select statements that were uncacheable. So fragmentation can be a problem. Fragmentation can cause quite a bit of extra work for your server. And you can avoid it by tuning the block size. So what you want to do is set the querycache min res unit. I always forget how that goes. The querycache min res unit server variable to the correct size. You want to try and set it close to the average size of your cached query. And you can actually examine the query cache and figure out what the average size is. And you may need to tinker with it a little bit after that. But one good way to avoid fragmentation is to pick this so that it's not too small and not too large, right? If you pick it so that it's too large, you're going to potentially be trimming a lot of space after that last block is filled and leaving yourselves a lot of places where you can't fit any more memory. If it's too small, you're going to have to do a lot of allocations and a lot of searches for free blocks. Does that make sense? One other interesting hint, if you have a mixture of queries that are of various sizes and you can't pick a single block size, a single query cache min res unit that serves them all well, you can actually set the server's query cache type to demand, which means only cache this if I ask you, please. And then you can specifically select which queries you want to be cached. For defragmenting, there is no defragment or cache command, but that's what flush query cache does. And flush query cache always gets me because I think it means flush everything out, right? Well, what it actually does is it goes through and kind of compacts everything and moves it to the top of the pretty blue rectangle that I've been showing you. However, there is a single global mutex on the query cache, and this applies for every kind of operation, including selecting from and storing results to it. When you're doing this flush operation, which compacts your memory, the query cache is locked for the duration. And that, in practical terms, means that your entire server is locked, because queries that might store results to it or read results from it are blocked because they're going to wait for that mutex. And update and insert types of queries that might need to modify to throw out some cached results are also going to be blocked.
How long does that typically take?
You'll have to time it on your workload and see how long it takes. It depends on how large your blocks are and how many of them and so forth. I'll mention later in the slide. Typically, yes?
Is there anything that disables query cache per session?
Is there anything that disables the query cache per session? Yes, the query cache type variable is configurable at the global level and at the session level. So the question is how long it takes to flush the query cache, and it really depends. we found that making your query cache larger than about 256 megabytes can cause it to stall for a considerable amount of time. And that's obviously dependent on your hardware and your CPUs and all that kind of stuff. So here are the server variables that you can tune to influence your query cache. Go ahead.
Sorry, to combine the two, could you disable it in a session-based way and then flush it, let it flush, or do you still have to hit the effects if it's disabled?
You can disable it on a session level, but... sure, yeah. The question is, can you disable it on a session level and then flush it, thereby avoiding the overhead of having everything block on the mutex? You can disable it on the session level, but since the session level variables inherit their default value from the global value, you would have to wait for every existing session to close and reopen with the new value.
So yes, but no.
Right. Yes, but. So when, yes. So you're asking if you disable the query cache for each session. Yes, that's true. Even if it's disabled in the session, if you run an update, it will still have to wait for the flush to continue. Yes?
Is there no way to, I'm having trouble understanding why it's blocking. Is there no way to say, here's the amount of memory, here's the whole chunk of it. If I want to flush the query cache, just turn it off, leave off so no one can use it, and then from the right totally blank. So you're starting from scratch. There's nothing to collect. There's no reason to look at each page or something like that, right?
It's kind of a difficult problem to solve, I think. There's probably a better way than it is currently done now. But when you're dealing with concurrency and memory management, it's non-trivial. Okay, so these are the variables that you can tune. As you can see, there are not that many variables to tune. There's the query cache limit, which is the largest. I think I've got the... nope, I sure don't. Okay, the query cache limit is the largest query that you're going to permit to be stored in the query cache. The minimum result unit is the initial block size when you're storing results. The query cache size is the total cache size in bytes for the whole server. Again, for that entire big chunk of memory. The query cache type can be on, off, or demand. Demand means don't cache anything unless I tell you. And the query cache write, lock, invalidate is the only thing that makes the query cache potentially behave somewhat differently from changes the semantics of the server when the query cache is enabled. This controls whether you can get results out of the cache when someone has a lock on a table that has gone into that cache. So you can tune that so that you can get results for a select query even when somebody has locked the tables from which that select query came. So hopefully this can be seen at the back of the room. If not, I'm afraid I can't do anything about it. So here's a little flow chart for how you can tune the query cache. Start at the top left in the box labeled Start. And go right down to the first diamond. Is the hit rate acceptable? So I showed you a formula earlier to determine what the hit rate is. If it's acceptable, you're done. Okay, if you're getting good performance and you have no complaints, you're done. No need to tune. If not, then you have to look at, well, you can go at this several different ways, but here's the way I suggest at it. First, look at whether most of your queries are uncacheable. So do you have a lot of queries with current time or something, or RAND, or something like that in them? If you do, then the query cache limit may not be large enough if the hit rate is unacceptable. Now, there's a lot of logic into why that might be true, but actually, this might be a little difficult to explain to you. If your queries are, if you're not getting a good hit rate and your queries are uncacheable, then you may not have a large enough query cache limit. So you've got to look at that and see whether you need to increase your query cache limit to let those queries be cached. Then you can look at a lot of other things, such as whether there are invalidations, is the cache warmed up? And by warmed up, I mean, have you actually been putting results into it long enough that you can get the results back out? Is the cache fragmented? You can check that by looking at the ratio of the free blocks to the total blocks, as I mentioned before. Are you seeing a lot of invalidations due to low memory? And are you seeing a lot of invalidations due to updates? So any of these factors could make your query cache hit rate less than you would like. In practice, looking at the query cache hit rate is not necessarily the best way to tell whether your query cache is really working well for you. One of the best ways to do this is to simply look at whether your server is performing better with it on or off. I've seen cases where people's servers were using a lot of CPU because they had the query cache enabled, and I said, please turn that off and let's see what happens. And they didn't want to do that, and I said, well, I'm just going to turn it off anyway. Immediately CPU usage goes to the floor. And I said, look, CPU usage went down a lot. You are really incurring a lot of overhead with your query cache here. You either need to tune it or just leave it off because your workload may not support caching very well. So that's another question to ask yourself. Can I really cache my workload? Let's say you've got 500 megabytes, which is an enormously large amount of memory devoted to your query cache, and you're running a whole bunch of updates and occasionally running a select. You're going to be incurring a lot of overhead because every update is going to be checking, is there anything I need to throw out? Is there anything I need to throw out? Occasionally a select is going to come along and say, all right, you put something into the query cache, and instantaneously it's going to be thrown out by another update. Does that make sense?
Updates from replication threads invalidate the query cache?
Updates from replication threads do invalidate the query cache. Yeah. Yes?
Can you what's considered an acceptable hit rate?
Good question. What's an acceptable hit rate? It depends on your workload. Something that I haven't really gone into a lot is that you can segregate your workload, and you may have, for example, a lot of queries that are uncacheable against certain tables and queries that are very good to cache against other tables. So these variables that I showed you are global. They're server-wide, and they show you on the overall level how your cache is doing. But they don't tell you, you're getting a lot of good usage for the cache out of your, your users table or something like that, whereas you're not getting good usage for your messages table. So you actually have to look at your queries individually and try and figure out whether they are cacheable. And that's where setting the cache type to demand and then specifically asking for certain queries to be cached can make a lot of sense if your workload doesn't work well with that. In the back? If you have the query cache enabled at all, there is still an overhead on updates. So the question is, if you set it to demand, is there still an overhead? And the answer is yes. Yes? The cache has no TTL. That's a great question because most caches have some sort of expiration policy, right? There's no expiration policy. The expiration policy is when I need space, I'm going to throw out the oldest. So it's least recently used, but that's not really expiration. That's a reuse policy.
If you have logs in your tables and they fit in the cache, they will be part of the result. They will be there.
So the question is, if you have blobs in your table and they're part of the results, can they be put in the cache? The answer is yes. Anything that can come back in your select statement can be put into the cache. At the level of the cache, there's no concept of rows and columns. It's just bytes. That's kind of one of the important things about the cache, that there's no overhead for example, for converting a column into the desired character set or something like that. You just send back the bytes. Another?
When I was asking about fragmentation, you said how doing a flush cache locks the server. Is there a way to instead just actually empty the cache and start it building up again without locking the server? Or would there be a benefit to that, perhaps?
There is a way to immediately discard the entire result sets, everything that's stored in the query cache, and that is reset query cache. So I'm not sure whether it does that incrementally or perhaps just frees the memory with free and then reallocates with malloc. I'm not sure how that works. Okay, so let's look at how initd works. This is kind of interesting because the MySQL manual says, starting in version 4.1, queries that use InnoDB tables inside of a transaction can use the query cache. and that's all that they say. So we looked in the source code and talked to Heikki Turi, the creator of InnoDB, and his team to try and figure out how this really works. So the way it really works is a little more complicated than just queries can use the cache. So my cute little thing here is that it works for some value of works. InnoDB actually tells the server whether a table is eligible to be cached. Okay? So the server says, are you cacheable? And InnoDB says yes or no. And that affects both storing results and reading results from the cache. So if there's a query cache hit, a select statement comes in, the server says, yes, there's a matching query stored in the cache, and here's the list of tables that it affected. The server goes through each of those tables and says, is this table eligible to be read from the cache? If it's an InnoDB table, it actually asks InnoDB whether it's okay to read that result from the cache, and InnoDB says yes or no. So there are two factors that determine the yes or no. One is your transaction ID, and the other is whether there are locks on the table. This is kind of a coarse heuristic. You probably know about InnoDB's MVCC, multi-version concurrency control architecture. There's many, many complicated situations that you could dream up where a query would return the same results that are in the cache, but it's very difficult to actually determine precisely yes or no. So this is a rough heuristic for I think so. If the result is no, then you can be guaranteed that it's true, but you might also get some false no answers from InnoDB. So if there are locks on a table, it's not cacheable. The code that says yes or no is actually pretty clear on this. If there are any locks on the table, return no. And if the table's transaction counter is greater than your transaction counter, then the answer is no. So let me explain this a little bit more. Each table in InnoDB, only in memory, not on disk, but each table in InnoDB's internal memory structure has a 64-bit transaction ID counter on it. And when a query updates, when a query commits, a transaction commits, let me get that right. When a transaction commits and it was holding locks, InnoDB releases those locks as the transaction commits. And for each table that it finds locks on, it updates the table's transaction counter to the transaction ID of the system. Not the transaction that's committing, but the transaction ID of the system, which is the newest transaction in InnoDB. So in practice, what that actually means is that if you're transaction 1, and you're updating some things and you've got some locks on a table, meanwhile transactions 4, 5, 6, etc., all the way up to say, let's just say transaction 10, if those transactions come in and modify the table, when transaction 1 commits, that table gets transaction ID 10 stored in it. Suddenly, everything less than 10 can no longer read or write that table from the query cache. Does that make sense? This last thing I said here is actually kind of funny. That doesn't mean quite what I mean it to. It doesn't quite say what I mean it to. I'm saying if you modify a table, you can never read or write it again until you start a new transaction. Well, you're committing, so you're starting a new transaction, right? So there's a few kinds of optimizations that you can make to the query cache, and we've already gone over some of those. One of them is simply maintaining it and making sure that it stays defragmented, analyzing its performance, perhaps analyzing how you use the query cache. One helpful thing, which I'm not going to suggest that you use many small tables instead of one table just so that the query cache works better for you, but if you have many small tables, your updates against them will be constrained to less data. So let's say that you have an archive of messages. If you have that split out by day, and for some reason you are updating your archive of messages, an update to any particular table is only going to invalidate 1 day's worth of cached queries. If you had all of those messages in one table, you'd be throwing away every query that touched anything in that table. You can also batch writes together. So instead of doing single row updates or single row inserts or something like that, you can use the various statement syntaxes that MySQL provides to let you update multiple rows at once. That way you're doing less work because you're not, for each statement, for one thing, throwing results out of the query cache, and for another thing, checking to see if there are any results to throw out. And I also already mentioned you shouldn't make it too big or you may see it stalling. In that case, you can actually see queries waiting for the transaction, waiting for the query cache to become available to them. And another thing that I said was that if your workload isn't benefiting from storing results in the query cache, don't enable it. Save the memory. And to do this, you actually need to set it to off and to set the query cache size variable to 0. I saw a hand here.
When something is waiting for the query cache, when you do a process list, does it show it as a special...
Does it show it as a special status when it's waiting? I'm not sure. Does anybody know? It does not? You haven't seen it. Okay, so when you're looking at process list and something is waiting, you don't have any indication of what it's waiting for. Okay? Keith?
You mentioned, let me just ask this. Is there a percentage that's too high for your hit rate? Another, maybe, I don't know.
Is there a percentage of hit rate?
In other words, is my cache too, I don't know if that makes any sense. So we actually, on our servers, we have a really high, I think it's like 97, 98%.
Congratulations.
No.
Is there a query cache hit rate that's too high?
Yeah. Does that make sense?
I'm trying to think of any cases where that could be a bad thing, and I can't think of anything. Yes?
In 5.1, when you say many small tables instead of one big table, 5.1 that we partitioning, would that be the equivalent of many small tables?
Okay, good question. In 5.1, partitions are conceptually sort of like many small tables, right? So is that equivalent of splitting your tables into many small tables? As far as the query cache is concerned, it's not, because logically, those partitions are one table. So they will be, for purposes of query cache, MySQL treats invalidation and storing results from that table as though it's one table. Yes?
You have not mentioned the 256 megabyte number, but where does that come from? I mean, situationally, how does that adjust with what you're actually serving and what you're actually...
I pulled that number out of the air, actually, because some of my colleagues had experience with it and said, 256 megabytes looks like around the largest size that's practical that they have seen.
What are the things happening when you go down to that would cause great performance?
Okay, so when you have 256 megabyte query cache, what are the things that could happen that could cause a performance rate, the performance to an as a result of it being 256 megabytes? The main thing is that since MySQL is using a fairly simple memory allocation, you can look in the if you really want to do this, you can look in the comments in the header of the query cache code, and they've got all sorts of nice little diagrams drawn to show you the structures. Looking at that will give you a sense of the complexity of managing this memory. There's all sorts of linked lists forward and linked lists backward and cycles and things like that. And it's just the complexity of having all of those objects in the cache to manage that really adds the overhead. So the bigger your query cache is, the more objects you've got to manage there and the more complexity. Yes?
Is there a way to manually declare a query that's important to you, like account something expensive, and when it's invalidated, instead of invalidating it, it should be updated?
Is there a way to update instead of invalidate? No. For that type of situation, when you're caching something that's important to you and you want to control when it gets expired, a better idea is to use a summary table. So take that very expensive result and cache it in a table instead of in the query cache. And then you can control when you want to regenerate it. I saw a hand over here.
Just kind of a follow-up to the first question about 256 megabytes. It sounds like from what you're saying, the number of queries that are stored reaches a limit and not the actual amount of memory. Or am I hearing you wrong when you're talking about the structure? You're saying that the structures grow too big. So
there become too many of the structures. And for example, one thing, you can tune down the size of those blocks in there with the query cache min res unit variable. That means that you're actually going to be storing, you're going to be chopping that memory up into smaller chunks, and there will be more of them. And that's more work for MySQL to work with. So it's the number rather than the actual size that really makes it inefficient.
storing, for example, like 1 meg result text, I mean, could you go bigger than 256 then? Because you're only storing 256 objects.
Okay, so if you have 256 megs of memory and you decide to set that variable to 1 megabyte so that the blocks are initially 1 megabyte, yes, you would only manage to fit 256 blocks at most in your query cache. Actually, it would be less than that because of the overhead of the housekeeping structures. However, if you store a query that is 1 meg plus 1 byte, MySQL will take a 1 meg chunk, fill it full, and then it will take a 1 meg chunk and put 1 byte in it, trim it down to 1 byte, and now you can have 1 meg minus 1 byte of free space that might be unusable. So that's the trade-off there. Let me see where we are in time. It is 10 till, and I think that's the limit, isn't it? Can someone confirm or deny? Okay. Well, thank you very much, and more questions outside if you want. Let me get a Percona t-shirt if you would like to. So go ahead.
More t-shirts per session at this one.
Yeah, that's right. I get more teachers in sessions than in the...
Up there?
I guess
The work day's over, maybe they'll stop putting these.
Howard, stop.